Okay, this is the last subtopics on the strengths and loading kind of the random variable situation. Correlated case. This correlated case, this will include this afternoon's of course, exam. Exam is pretty straight. Timing is all set, and it's not going to take really over 2 hours. If you spend over 2 hours, something is not right. So this is kind of the last topic, but I want you to understand. I'm not saying same problem gonna appear in the exam. I'm not saying that. All the elements is what you should know. And the correlated case, so this is actual stress sigma y correlated case. So before we do get into the formulation, I'm going to bring back the M. What's the M? Safety margin. So safety margin using the same notations we are using right now, M is equal to, before I use like R minus S. That's one type of the notation initially I was using it, but it shouldn't matter, right? What the notation we are using it is yield minus sigma S, right? So nothing to confuse it. And then variance. What's the variance? What do you call the variance? Standard deviation square, that's what the variance. And that's what the variance is. And the variance M, so I can use like variance M. Yeah. Variance M is equal to e to the what? M minus mu M squared. Given, right? Or this guy you can write as minus infinity to infinity M minus mu M square Fm. Should I use M? Should I use X? So let me use, oops, I'm sorry, what am I doing? Maybe M. What's that? That's a definition, going always back to the definition. Or I can write this guy as E, and M is R minus S, isn't it? Or let's use the present notation. we are using it is mu y minus the sigma s. I'm going to put this way. Minus mu y mu s. Correct? If it's wrong, you let me know. Square. Put it back the components right in. And this is equal to e to the, now this guy is square, mu y minus, this is surely Friday morning, isn't it? Y minus mu s square plus, is it correct? Oh, instead of, I'm trying to derive to get the expression in terms of the random variable related to random variable. So I'm gonna take this guy associate with the y, this guy associate with this guy. So now this is s, and the minus, oh jeez, gosh, this is a disaster, isn't it? Y, right? So this is s minus mu s square. Reverse. Correct? Okay, so now I'm going to open the bracket. So e to the sigma y minus mu y square, right? Plus mu s minus sigma s minus mu s square minus 2 sigma y. If I make a mistake, you let me know. Right? Now I'm going to apply expected value to each term. So this is equal to minus mu y squared, first term, right? And plus e to the sigma s minus mu s squared minus 2 sigma y minus mu y sigma s minus mu s. That. So what do you call this? Which is called the variance sigma y. And plus, what do you call this? It's a variance sigma as actual stress. Okay, this is a yield to stress minus 2. What do you call this? It's called covariance. Covariance of sigma y and sigma s. So this is called the covariance sigma y sigma s. So here, if sigma y and sigma s are independent, statistically independent each other, or mutually exclusive, it's all the same meaning, mutually exclusive, then which term gonna go away? Covariance, okay? Because covariance is kind of showing the relation between the two random variable. If you look back your notes, maybe a few weeks back, you could see the rho xy. What do you call the rho xy? It's a correlation coefficient. You remember? Is equal to sigma xy over sigma x sigma y. You remember this? So what do you call this guy? This is covariance. So over here, the notation I'm using, the reason I'm using this notation, that notation, I pick out really few good reference book, then I reviewed it, then pick out the best features. So each textbook they use a different notation. Then that's what it happened. This is equal to exactly the covariance of, in this case it's gonna be xy. In this case, it always equal to e to the x minus mu x, y minus mu y. So this guy is a standard deviation, so which is equal to square root of the variance of x, and this guy is equal to square root of variance of y, right? And this is a degree of correlation between x and y, the random variable. What's the range of x and y? What's the range of rho xy? Minus 1 to 1. Looks like Kiwan is ready to take the exam. But who knows? So the range of rho xy is that. Okay, and so you know the expression. This is expression for the variance of m. M, using the notation m, will slowly come into picture. So this is a variance m, and using standard, I will write this name at least 5 more times before end of the semester. Standard normal distribution function, using the standard normal distribution function. First order reliability, second order reliability. Everything is based on the transformation into the standard normal distribution function concept. Everything transform into you. You know, many things happening to facilitate the computation. For example, another example is, how many of you took the vibration class? No vibration? Who cares? No dynamics? No dynamics. in the dynamics of vibration or structure dynamics, everything is coupled. All the problem set is a coupled problem set. It's interconnected. If you push the one point, then of course the point away from this point, if I push it, influencing or affecting the point in another location. Why? It's all interconnected. So when you take a finite element approach, then you have to consider the non-zero entry in the stiffness matrix or mass matrix. Look at me. So everything is interconnected. So you always, when you set up the equations of motion, you always has a coupling term. In other words, a off-diagonal entry, if it's equal to 0, then what happened? It's very nice to solve the problem. Off-diagonal is equal to 0 means then you have a whole bunch of the independent equations of motion. You have a simultaneous equations of motion, simultaneous sets of equations to solve. If off-diagonal is all 0, each equation is independent each other. It's all bachelor. It's not married situation. Then you can solve one problem before the breakfast, after breakfast, vice versa. So to make life easier, long time ago, people introducing so-called the modal transformation. You heard about it? Songtae, never heard? Oh. Yunsuk, never heard? Who cares? Well, in other words, all the coupled equations of motion, you try to transform into the other space called the modal space, then you can really get all the off-diagonal terms set equal to 0. Then each line of equation is independent each other. Then you can just solve one at a time, any time, because coupling is all gone in that space. It's called the modal space. I think in undergraduate, lots of, like mechanical engineering, it should be required. Higyo, you take a vibration class in undergraduate? Yonghyun, how about you? In academy, who cares? In Naval Academy still, they took the, how about Kyungsuk? Oh, you didn't take in Hanyang University? No? How did you graduate? Yes or no? Oh. Might be a good idea. Oh, it's not mandatory because this department is not the mechanical engineering department or aerospace. Mechanical, aeronautical, mandatory. I can say that. How about Ilyong? Not taking? How about Hyun? Professor O is teaching the vibration relevant course. It's like a vibration or structure dynamics in ocean systems engineering. Might be a good idea to take, even if it's not directly related to to your major research, or it's a selling point. I think Mr. Nang will delete afterwards. This spring, Yun-Suk took the course I'm teaching last year, but I'm going to really do a little bit update on the random vibration. That's really random vibration class, and take that course. This is kind of a continuation of this class. It's called stochastic, I forgot the name, stochastic theory, stochastic theory of structure analysis and design. And it's a fun course to try to deliver what happened, how the system responds in the random situation. Not the regular input force. No, it's random. Then how the output would be. Don't you think it's interesting? Sangtae. It's interesting. You know, our body, physics of the body, we always like to have particular rhythm. You know, I still have a twin daughter. They're all grown up, about your age. When they are like 4 or 5 years old, when I turn on the classical music in the living room, they just sat next to me. They don't react on classical music. They sit there, do nothing. But when I turn the rock and roll, fast music, K-pop, you know, 소녀시대, then they are crazy. They all, you know, they can't just sit there. They get up and really twisting their body, you know, because their modal frequency is pretty close to their body frequency. So every one of us has a body frequency. Then you have to know what that frequency is. And what happens if it's a random situation, random kind of the frequency type music, how is it going to react? Your body would react. That's what the random vibration, stochastic process, dynamics. This course is strictly statics. So that's what the selling point. So that's what. So what am I doing here? Then everything is transformed into the space which decouples the random variable. That's what I'm heading from next lecture, from next Monday. Decoupling, that's a trick. It's a slick trick, okay? So-called using the Rosenblatt transformation, which was, I didn't know about the Rosenblatt transformation. It's a fancy name, but the person called Rosenblatt, he's a mathematician. He discovered or formulated this Rosenblatt, doesn't have to be Rosenblatt, transformation to the space where all the system variables are decoupled. If it's decoupled, very nice to solve the problem. I'm keep telling you, just pouring down the concept. You know, the problem for structural reliability is to solve the problem of integration, multi-dimensional integration. Is it problem? It's all coupled, tangled up. It's not the parents plus 10 children, no. It's the mother and father, maybe 100 children. It's all tangled up. Then when you throw that random variable with a formulation, throw into the space, then you can really nicely arrange all the variable, random variable, independently each other. Then you can convert the integration of the multi-dimensional probability density function into the multiple integration of individual the probability density function, which is really nothing but the multiplication of each integral to get the structural reliability. You get the idea? That's where we are heading. So this standard normal distribution function simplifies the stuff in the real world, throw into the world where everything can be decoupled. So in that sense, this is very kind of important, and people just keep using it all there. So PF really doesn't make any difference whether I'm dealing with a PF or R, right? Why? PF is equal to complement of R, right? So it's 1 minus R is PF because it's complement each other. So here is probability. I wrote this at least I feel 2 to 3 times. Can I do that? Yes. And this guy is sigma y minus sigma s. When this guy is less than sigma s, if this guy is less than that guy, that's a failure. Easy to remember. So this minus infinity to 0, then Fm m dm by definitions, right? Because this is up to the 0. For probability function, if it's like this is mu m up to here, which means this is nothing but the area up to the 0. Then this is equal to minus infinity to 0. Then you have to bring the normal density function, right? So normal density function, I have to write this guy as a sigma m 2 pi 1 e to the minus m, variable is m, minus mu m square to sigma m square. Sigma m here is of course the standard deviation stuff. And what else? Yeah. Then I can change this into the form minus infinity to 0 minus mu m over 2. 2 is gone, right? Sigma m. By the change of variables, you can put that in here. 1 over 2 pi e to the minus m square over 2 dm is equal. I don't have to write this guy all the time. I can just bring back the notation, the phi, right? Phi as 0 minus mu m over. Once I wrote in this form, This is a standard normal distribution, and whose mean is equal to 1, is equal to 0, and sigma m is equal to 1. And everything fit into this format. So probability of failure is equal to phi minus mu m over sigma m, or I can rewrite this guy. We have done this, but bring back here is minus beta. So over here, beta is equal to what? Mu m over sigma m. Beta is called reliability index. In other area processing reliability, are you using the beta? Have you heard the reliability index? It has some history. I mentioned to you the first person who used this term is Alan Cornell from Stanford. He disappeared, as I mentioned. I don't know where he is. He's gone. But after that, after him using quite a bit. And not only equation is important, always look at what does it do in terms of the engineering. What does it do, you know? Mu, for example, this is normal distribution. This guy is a mean of m. And from here to here, if you take mu m is equal to beta times sigma m. How many standard deviation to get to the mean? So this is like beta times sigma m. From here to over here. Of course, dispersion. This dispersion is the value of a standard deviation. How good that is. So if I finally rewrite everything here is phi minus beta. That's end of it. Very nice expression in terms of normal, standard normal function. And if you look at the book, chapter 5, this particular section, their final equation seems to be wrong. And in my lecture note, you can check back. I'm going to do a little bit here. I think equation there is wrong. You know why it happened? Usually students, they derive the final equation set maybe they try to solve after 1 p.m. Not 1 p.m. After midnight, 1 o'clock in the morning. Maybe that's maybe that may be a problem. So beta is equal to mu m over sigma m. Definition is equal to expected value of sigma y minus sigma s And what about the sigma m? Square root of square root of variance y minus 2 covariance sigma y sigma s plus variance of sigma s. We have done the derivation this morning. Redo once again. Okay. Then I'm going to multiply here as 1 over E sigma s 1 over E. Would you really take the course, as I mentioned before, really doesn't matter, at least what our department professors are teaching, like Professor O's, like a dynamic, so structural dynamics in ocean systems engineering, or my course on spring, things like that, to get completeness on the dynamics problem. In Professor Chang's research project, of course you need, when you get out to the real world, you need dynamic behavior, because ocean environment is a dynamics, it's not the statics. Design, ship design, of course, is done by statics based on the long history, but you are dealing with a dynamics problem. Don't look over. You will feel sorry after you finish and tossed out to the real world. Then too late. Then don't feel, oh, I have done all the requirement of the coursework for my degree. My answer, who cares whether you finish or not? If you feel it's necessary, then take the course. Dynamics course in addition to statics course. So if you multiply up and down like this, okay? I'm not going to rewrite, it's in my note. I want you to really conform, but numerator, you have E, the sigma y, sigma s, minus 1. Then this is long, the denominator is rather more terms in there. If you have my notes, and please really conform that. Then if you do that, you can have all that, right? If you do that, you have this. And this is N1, right? What's this guy? It's a central safety factor. And you have, this is different from the solution in the book. But I think his students may screw up. Or I could screw up. So let me know. But I reconfirmed myself. I didn't ask my teaching assistant to Higyu redrive it because I was sure this is correct. please conform yourself over here, mu y, the sigma y, sigma. This is covariance. You will get the simple problem set on the covariance. So here is, so this is beta. Beta you need because phi minus beta is equal to pf. So here is n1. And this guy, coefficient of variation, this guy and that guy. This is the coupled situation. No correlation, second term drops off. Messier, much, much more messier. And I made a copy, nice color copy, in the file that I sent you, of course, has all color you can see, but this is what the reliability space, structural reliability. I made a color copy because next Monday I'm not capable of drawing this on the blackboard. This semester I don't want to use PPT. Totally I want to avoid it. Then whenever the need arises, then I'm going to give you a copy. Then we can all look at together. So bring back this next Monday, then I can explain better. You have my all the file I send you, so I'm not going to give you my the copy of my lecture note. So okay, even if this is a 10:45, I'm going to stop right here. And any questions? Two variable problem, all the concept, you should really follow the structural reliability concept as of today. So now, from now on, getting into the approximation technique, then we can really solve complex problem. And in addition, around mid-November, I want to assign the semester-long term project using the first order, the reliability method. Then thinking about, I want as a group, think about the problem set, multi-dimensional problem set, if it's possible in your area. In your area. Then I want to have a proposal. You have to think. Multi-dimensional means M is R minus S. R could be one random variable. That could be a collection of the random variable. Depend on what you assign the random variable. You can say dimension could be a random variable, or Young's modulus could be a random. So a lot of different things you can think of. Not 100 random variable, then you can solve maybe at the end of next year. Too late. So reasonable number to catch the concept and also apply in your area. It doesn't have to be the reliability problem, but still within the content of this course, reliability problem is what we want to handle. Got it? So think about it. Then propose your, I can reject it, then you have to redo. Then we'll go. When I say mid-November, by the time you could catch the how to handle for multidimensional space. Okay? All right, so I'll see you